So I'm now going to present some of the work that we've been doing as part of our collaboration I mentioned, and I do want to thank and mention all of the people, some of whom are in the room, Roger Whitehead, Stuart, Glenn from the Hintonwood Products and others who are intimately involved in this project. UBC was involved, but it was led by FP Innovations and the Canadian Wood Fibre Centre. Essentially, as part of the project, we processed and worked with them on the LiDAR holdings of their entire FMA. So you can see here the area of that FMA, 990,000 hectares, 385,000 AVI polygons. We did an airborne-based analysis of this work and then some ground-based analysis of this work as well. So that's the location of the FMA within Alberta as a whole. Obviously, the company has its own significant amount of fibre data and growth plot data within the area itself. And then we have the LiDAR data, which was available, collected between 2004 and 2007, around 1 hit per square metre, immediately telling us that individual tree-based work would be very difficult at that scale. We automatically start to think about plot-based relationships when we're seeing that type of density of data. So we did most of our processing on fusion. I've got a couple of slides about fusion at the end, so I'll talk about that for you. But fusion's able to give us very easily all of these spatial metrics. So fusion can give us all the percentiles, it can give us height, it can give us cover at any type of sponge level that we want. All of these different variables can be easily derived from these types of packages. And then the work then was to relate the airborne plot metrics that we derived from the LiDAR data with the field-based permanent plot data that we had from Hintonwood Products. In this particular case, the models, 3 sets of models were done based on species. So the AVI was used to stratify out the 3 major species groups, and that then defined the 3 major models that were set up, coniferous leading, mixed, and deciduous leading. And then in this particular case, rather than multiple regression, some type of random forest, which is like a decision tree technique, was used to try to make the predictions rather than using a regression relationship. So over these spatial layers, they were put into fusion. These layers were then done, and then these models were then run predicting the variables that we cared about: top height, mean height, modal height, photometric mean diameter, basal area, total measurable volume, total above ground biomass. We have all of the variables from the LiDAR data of the forestry, but then, as you heard yesterday, we also have a stack of variables that we can get from the DEM itself. I had a slide there that talked about the accuracy. It isn't on this particular one. So the accuracy, when Hintonwood Products went to go and look at that, was very good. What they did was compare the estimates of volume that came from the LiDAR data to the estimates of volume from harvested stands. And they found that over a range of different density and stocking type classes, that there was a very, very good relationship between what the LiDAR predicted the volume was and what the volume was once it was taken off the truck, taken from the trucks off the stand. And in fact, there was no significant difference between what the LiDAR was predicting versus the standard methods of measuring that. So that's the airborne-based way of looking at forest inventory. I also want to give you a touch of a flavour on the wood fibre attributes as well, which was also collected at some of these plots. So wood fibre attributes are actually the attributes of the timber itself. And there are a number of attributes that are collected by people interested in wood fibre. I've made a bit of a list there. And across the estate, there are a number of plots that had that information available. The way we processed that data was we tried to look at the dimensionality of those 6 variables and then compared that to the dimensionality of the LiDAR. So we did a principal component analysis on those wood fibre attributes. I don't really want to make this too complicated, but rather than going away and trying to say, okay, we're going to develop a separate relationship between density and LiDAR, fibre and LiDAR, coarseness and LiDAR, modulus elasticity and LiDAR, perimeter and LiDAR. I mean, that's crazy. LiDAR's not going to be able to predict directly all of these internal wood fibre attributes. But our idea was, well, if we have these 6 different attributes, maybe they condense down into a couple of general sort of components. So if we do a principal components on the data, we essentially come back with, on just the wood fibre data, we come back with two types of indices. The first one was a weighted combination of those 6 that gave us an idea of the density and the stiffness. And the second one, when you look at how it weighted against the first 6 input variables, it came back as strength, smoothness, and softness. So the idea was, if we have these 2 principal components, can LiDAR predict them? Let's stop LiDAR trying to predict all 6. Maybe LiDAR can give us an indication more broadly of those 2 general components of the data. Before we did that, we actually compared it against the inventory data. So on the PC, just to remind you, this is the wood fibre attributes. There's no LiDAR on this slide at all. This is the wood fibre, characterised as 2 components, one based on density, one based on smoothness. And then on the top axis is actually the field data for that plot as well. So this implied to us that some wood properties correlate very well to the growth increment. I'm sure the foresters in the room are going, some of the PC properties, some of the properties of the wood fibre relate very well to the increment of the growth, and some of the wood properties relate very well to the current standing structure of the stand. So this is interesting because this sort of implies that LiDAR is going to be very good at giving you some of these wood fibre attributes because LiDAR can predict height. But there are still some wood fibre attributes that are going to be hard to get from LiDAR because LiDAR doesn't predict increment. So this is just again the Hinton Wood Forest, the Hinton Wood Products area, the FMA. These are the LiDAR attributes that come out of something like Fusion. We then went away and tried to say, okay, how well can LiDAR look at those different wood structural components? And see here we've got our strength and stability as our first component, cell structure on the second, moderate level correlations. So, are we able to directly predict wood fibre attributes from LiDAR? No. Do we think that there are probably some inherent correlations that we can rely on that give us an idea of the wood structure itself at this airborne type level? Yes. And it's interesting, I think, that some of those seem to be so highly driven by the current structure, and some of those are so highly driven by the increment that forest is actually growing at the time. So we went away and we used these 2 predictions to go away and make a spatial map. Different colours here representing then different levels of fibre strength and smoothness, or wood strength, stiffness and yield. All at the airborne level. More work is needed, but it was an exploratory study, and I'm happy to talk to you more about it if people are interested in how we went about that and other ways we could try to test and use that. Okay, 45 minutes on airborne. I've got to get through ground-based and space very quickly. Ground-based LiDAR. So, ground-based LiDAR, also called terrestrial LiDAR, is becoming more commonly seen in remote sensing community and the LiDAR community in general. I think you got an explanation about these yesterday. There are generally 2 types of instruments. Some instruments do a full hemisphere. I'll stand back and give my graphic demonstration. So there are those ones, and then there are also ones that are more, perhaps come from a heritage of mining, where they'll actually do it as a straight planimetric. The data is obviously not planimetric, but you'd be looking at that wall. So essentially you would get a LiDAR return data set that might be this type of area. So there are 2 different general types of the way that people can collect the data. The instruments are still in the range of $50,000 to $100,000. I just made that up as I was writing the slide. People may choose to argue with me on that. They could be more. Don't think they're much less. Most of the systems are discrete return, which I'm sure you heard about yesterday. In other words, the pulse comes back, goes out, and the pulse comes back. It simply measures the response of the returns on that pulse. I think we will start to see more and more full wavelength ground-based systems, and I'm sure they're going to start to become more common. So here's just an example of a scanning one. This is the one that I've collected most of my data with, which was an Australian instrument, but there's only one of them. The other Leica and Regal are often very commonly heard brands who sell these instruments to give us this ground-based type data. This would be what a hemispherical LiDAR would give you, one that collected the whole hemisphere. So this is essentially akin to a hemispherical photograph, but here instead of seeing brightness, you're seeing distance. So objects that are, well actually this must be intensity, this is actually can't be distance. But you can see that we're actually seeing the structure of the stems and then the crown structure all collected by this LiDAR device, and every single return then is going to be the distance from where the instrument was looking out into the forest canopy itself. This is what it would look like unraveled. So this would be a projection, essentially, of what the 360-degree stand would look like. You can see here that we get a little bit of distortion very close to the ground. We get fantastic looking data sets looking out into the forest canopy, and then this projection, much like a Mercator projection, is going to get all funny with Greenland. So we're getting quite funny representations of the top of the crowns. It's all captured correctly though in this way of looking at it. It's just that when you display it in this particular way, you start to get significant distortions at the top of the processing. When we go away and calibrate LiDAR data sets, we often want to make sure we know what trees we're talking about, so we cover the trees in shiny reflective tape, and that's what you can see there. And then to make our LiDAR, we often do multiple LiDAR scans in a forest because the issue of occlusion becomes quite significant. You can't see through a tree if there's a tree in the way, so we take multiple scans. The way we register those multiple scans is we put polystyrene balls on sticks. So you can see there, 1, 2, 3, 4 polystyrene balls sitting on sticks that become our co-registration when we stick these LiDAR scans together. Another example of what a forest stand looks like. This is one of the, I think this is one of the lodgepole pine stands. We have been doing some work looking at ground-based LiDAR across a range of different stands. This is the McKay spit thinning experiment, Jim Stewart's work in Alberta. We can see here we took 5 LiDAR scans, so each corner and the centre, and then the polystyrene balls are allowing us to register all those scans together, and you'll get a data set that looks like this. This is all the ground-based LiDAR scans that we're getting back through the plot. This is the different scans we get for different levels of stocking. So these stands from the bottom are 750 stems per hectare, 1500, 2600, 3700 for control. And you can see here we're clearly getting, obviously, we're clearly getting the structure of those stands very, very easily from this ground-based LiDAR approach. We go away and we do very similar than we do with the airborne. We go away and group those hits and represent them as a distribution, which we're seeing on the right-hand side there. Yes, Bob?
How long does it take you to collect that data?
So it probably takes, well, it depends on the instrument. It depends how dense the data is being collected. It depends if it's a full scan or a big scan, but less than half an hour. So it's becoming faster and faster and faster. With the instrument that we used that was quite slow, it was half an hour, so that's sort of like the maximum, I would say. So getting less than that per scan. So if you were going to then move around, then you'd be doing, 2 hours, 3 hours perhaps, if you wanted to get 5 scans of your particular plot. So you can see there the variations, of course, that we're going to get based on those different density classes. We've then been trying to, with this work of Jim Stewart, trying to compare the LiDAR heights again with the stand heights that we measure in the field, and this is actually a comparison between the airborne LiDAR data and the terrestrial LiDAR data, looking at a variety of different attributes: stand height, basal area, stocking, depth of crown, DBH. We didn't have many plots in this particular work, so most of our relationships are demonstrative rather than predictive. There's of course the opportunity to link ground-based LiDAR and airborne LiDAR. My PhD student did this the first week he was with me. I thought it was the best thing I'd ever seen, and I should have given him his PhD there and then, because he's still with me, and we haven't progressed much past this, but it is a glorious picture, I think, that demonstrates the unique power of both of the instruments. So the green is the ground-based, obviously giving you incredibly dense, rich information on the lower part of the forest canopy, and then the airborne, beautifully giving you these top canopy architecture, which clearly isn't seen by the ground-based, but then you can also see at what the airborne is missing in terms of the richness of the other canopy information within the crown itself. It's also fantastic to look at where the wire hits, so how far some of the wire hits have got down through the canopy, some of the stuff we are hitting, some of the stuff that we're not. So both of these if you accurately know where your terrestrial LiDAR scan is, you can easily produce these types of representations of your ground story and your overstory and your understory. Really quite breathtaking. So work in this area is looking at trying to bring those data sets together. The common sort of way of thinking about it is you would get your canopy from your airborne, you might produce a cone or a cylinder, and then you'd use that as a bit of a template to go away and cut through the terrestrial LiDAR data to give you the individual crowns. And this particular student's PhD is on trying to extract individual stem information from every single one of those ground-based hits. So we essentially come in, we use our airborne to cut the trees down, metaphorically. We cut the trees, we put all the LiDAR hits, and you essentially can populate every tree within its volume, and ultimately you're trying to derive individual stem information from the terrestrial LiDAR data itself. If you know where every tree is, you can then predict each tree, predict the DBH, and then compare that to a stem-based map. And then once you have the trees, you can then predict the DBH against the field DBH. So if you've got very, very good terrestrial LiDAR and you've got a very good tree finding algorithm, and then you've got good, clear views of all of the DBHs, and you can assign the DBH in the field to the DBH from the LiDAR, and you can compare them, you can get a very good relationship. But that is an awful lot of work. Okay. Where are we going with satellite LiDAR data? So, we would love to have a satellite LiDAR, very much. We currently don't have one. The only airborne LiDAR data set we have, the only spaceborne LiDAR we have at the moment was called ICESat. It was launched by NASA, and it was designed to look at the height of ice in the Arctic and the Antarctic. As a result, it has a very big footprint. So I'm sure you heard yesterday about the footprints that we're talking about are dinner plates. These layers are the dinner plates coming through the forest canopy. The dinner plate of ICESat is 90 meters. So it's a huge circle. So they're trying to look at height changes in the ice in the Arctic using very big footprints. So this is the only LiDAR data that we have available from space. It's also not a wall-to-wall LiDAR. So LiDAR from space is profiling LiDAR. You have your little laser, which is my finger, excuse how it's pointed, and it will scan like this. So you'll get tracks of LiDAR data that will cross the Earth. There's none of this carry-on in space. It's all just a profile. Sometimes the system might have more than one profile. It might even have 5 profiles, but still, ultimately, you're getting single stripes of data from the satellite as it goes through the orbit. And historically, this ICESat satellite, which is the only one we've had, has a 90-meter footprint. So ICESat-1 has now been decommissioned. It doesn't work anymore, but the Americans are very happy with it, and so are the ICE people, and they're in fact going ahead and building ICESat-2. So that is the LiDAR data that is continuing to work in the ICE-type community. In the forestry community, there have been 2 attempts to launch, in the vegetation community, there have been 2 attempts to launch a spaceborne LiDAR. The first one was called VCL. It was about 15 years ago, and it was cancelled quite early in its development because of cost and technical issues. More recently, NASA went very enthusiastically after a mission called Destiny, which was going to be a combination of radar and LiDAR. The bill came in at over $1 billion, and NASA again cut the LiDAR component out of it. So there is no current plan from NASA to build a spaceborne LiDAR system. The Europeans have been considering it through their Earth Explorer call, which is like a call for small, quick satellites. None of them have made it to the final cut. It is a very expensive technology, and LiDARs, from my understanding, are incredibly temperamental. So if you put them on an aeroplane, it's okay, you can land a plane and try to fix it. Once there's things in space, you can't fix it. And there's a real problem with from my understanding, perhaps the reliability, but very technical issues associated with that. So if we're not even hearing about a system now, we're more than 10 years away from ever seeing one. So we're not going to see a spaceborne LiDAR specifically designed for vegetation anytime soon. If we do, it's always going to be a profiling LiDAR. So get out of your minds the idea that suddenly our bird is going to be covered in 25-meter spots from space. It's not going to happen. It's always going to be a profiling type technology. But you'll say to me, Nicholas, I saw this on CNN. In July 21st, 2010, NASA images used to map the world's tree heights. Very big in Vancouver, because I came back and said that, oh, the tallest trees are in the Pacific Northwest. So that was worth the $1.5 million. So this was the map that was produced by a colleague of mine, and in fact, Andy Hudak's, Mike Levsky. What he did was he used this ISAT data. So the ISAT data is far from perfect. It's 90 meters. The reason 90 meters is difficult in forestry is because we can't get the terrain accurately. The terrain is changing so quickly in 90 meters that it affects our ability to get height. But what he did is he used DEMs, high quality DEMs, and he tried to work out where in the Earth are some flat places, and tried to use flat places with forests to do it. But then he also had he sort of had a waveform that had all this slope aspect. He tried to remove the slope aspect by using a DEM. And by removing the effect of slope, he tried to come back with a broad estimate of tree height. And this was the map that was produced. It's at a 5-kilometer resolution, so it's completely unusable in any sort of operational context, but it is the first map of tree height for the world. So it is a remarkable data set in the broad context, collected by years and years and years of this ISAT collection, but very, very broadly collected. Okay, so in summary for my talk, now you have LiDAR data, what are you going to do with it? What is it? Well, I hope you have a fair idea of what it is. Can we trust the outcomes? Absolutely yes. For some attributes for LiDAR measures, it has become the standard. LiDAR measures things directly, and if we're trying to use those things that it measures directly, we're going to have a very, very accurate answer. Height and cover are the two best examples. Do we get unique information? Yes, because those estimates are going to be direct measurements of the variables we care about. What is the role in sustainable forest management? Well, I think it has a critical role, but it's important to remember that what LiDAR does, it does very, very well, but LiDAR doesn't do everything. And there's a couple of things that I haven't even touched here. Species, the word hasn't fallen out of my mouth, except when I talked about using the AVI to give a species to go away and develop a model. So species is a data set that you cannot get from LiDAR alone. You will need to link it with your AVI, your aerial photography, or your hyperspectral, or your multispectral, or something. Species is a very difficult attribute to try to get from LiDAR data set. And there are other data sets as well. Forest health is the other logical one that LiDAR data cannot be done alone. You need to augment it with other data sets. Where are we going in the future? Well, I think we're going to continually see more and more software packages able to accept LiDAR. Let me be quite honest and say, I'm not taking any more graduate students in my lab working with LiDAR, airborne LiDAR. There's no more research to be done. We know it works. The only LiDAR work I do now is people using LiDAR as a tool to answer another question. So LiDAR has almost become a base data set that we try to get to allow us to understand what something else might be happening. So that's how far we've come in terms of research around airborne LiDAR. Ground-based LiDAR has more work to do, but airborne LiDAR data, I think we're at the point where it's now a demonstrated technology, and that's why the companies, the software companies are really just accepting that, hey, this is a data set we now have to start to build tools around, because people are expecting to use it as a as a daily bread type data set that we read within. So that's one of the future directions, I think. We're going to see more and more software using more and more LiDAR. There's a bit of research going on into dual wavelength LiDAR. So you heard, or I think you've heard, that the pulse is in the near infrared. But there's no reason why we can't send a laser pulse in any wavelength. The reason it's near infrared is because we get maximum reflectivity of near infrared light from vegetation and most surfaces. So it's a good wavelength to use. But it's not the best wavelength to use, particularly. Different applications might actually have a better wavelength to use. So there's people building dual wavelength LiDAR systems. Ones that use the shortwave infrared, and ones that, and in bathymetry, ones that might use the near infrared and then something in the green. So we're starting to see dual wavelength LiDARs. In forestry, the reason we would be keen to see that is because we would get a different response of leaves versus bark, or leaves versus stem. Because in the shortwave infrared, there's a very strong difference between foliage and stem matter. So we would be able to get two distributions. One distribution of the returns in the shortwave infrared, one range of distributions in the near infrared, and we would get a foliage profile versus a non-photosynthetic profile. So this is the interest around dual wavelength. And a lot of people we're starting to see those being built, being tested, and I think that's what we're going to start to see as our ongoing data sets. Fusion of data sets with other data sets, I think, is becoming obviously a critically important thing. We're going to hear about hyperspectral today, and I'm sure many of you recognize and accept that LiDAR is only part of our inventory story, and so we need to work out how do we link it with the other data sets that still give us data that we need. So that's an operational and management topic that I think requires further work. And then the last one I hinted on was this idea of growth. So you're so lucky. You've got so much LiDAR data. We're soon going to start to have time series LiDAR. And in fact, I know you love to hear it, Alberta is going to be ahead of the curve in this area because you've got so much T1. So many other places in Canada and around the world are just starting to fly their first lot of LiDAR now. But here in Alberta, we've had LiDAR for what? 8 to 10 years ago. So we can start to fly it again, and we can actually start to look at growth. And that is an area that has very seldom been touched in the remote sensing forestry area, time series LiDAR, because we haven't had the technology for that long. So that, I think, is a tremendously exciting way to go. And what is the height increment versus the revisit time we need to be able to give us accurate estimates of height increment? And I think once we get height increment, that will be another tremendously important variable that LiDAR will start to contribute significantly to. Fusion is very good. People who like playing with software, it's free, written by the USGS. You can come and see me about it. You don't have to buy it. You can download it. It's got 2 modules. One is a GUI that you can fly through your data and you can see those beautiful trees like my golden spruce. And the other one is a very large command-driven part of the program that allows you to process data over very large areas. Anyone who likes to sit on their computer and play with geospatial data, who doesn't want to go and buy anything, should use Fusion. It is fantastic. I love it. I've got some papers. I don't expect you to read them here. Come and see me. And again, this is from our collaborators from the Wood Fibre Project. Reviews and all the work about the ground-based and the airborne. All of them have come out now, and I want to finish by saying that Silver Laser is the annual remote sensing LiDAR forestry conference. It's been going for 10 years. The first one was run by Mike Walder at the Canadian Forest Centre in Victoria 10 years ago. Every year it's gone around the world. We've been to Finland. Chris and I have been naked in Finland, naked in Japan, clothed in the US, of course, clothed in Scotland, clothed in Australia, of course, except that time later on. All around the world, it's been a fantastic conference, and we've actually brought it back to Vancouver, first return. Clever name. So, 10 years, we're having it at the Sheraton Wall Centre. I really hope as many of you that can come as possible. There is a trade exhibition, so people running private companies here. We've got booths available for people to come and display. It's a Monday, Tuesday, Wednesday. The Wednesday morning is going to be an operational morning. So talks from all around the world of people talking about operational use of LiDAR in a forestry context. So there's a website, www.civillaser2012.com. You are welcome to come. We would love to see you there. And thank you very much for the opportunity to talk.